Welcome to the Network Fundamentals series. I'm thrilled you're here diving into the building blocks of how computers chat across the globe. Today, in our first episode, we're unpacking multiplexing, network topologies, and data link protocols, the secret sauce behind efficient data communication. We'll cover FDM and TDM for squeezing more signals into one pipe, star, bus, and ring topologies for wiring up your network like a pro, and MAC protocols like ALOHA and CSMA to keep those data packets from bumping into each other. Whether you're a student cramming for exams or a curious tech enthusiast, stick around. By the end, you'll see networks in a whole new light. Let's jump in. Alright, folks, buckle up because we're kicking off this deep dive into why multiplexing is the unsung hero of modern networking. Imagine a massive superhighway with endless lanes, but you're the only driver cruising along. What a missed opportunity. That's exactly what happens in communication networks without multiplexing. Signals go solo, leaving bandwidth lying around unused. So, let's break it down simply. At its heart, the core concept of multiplexing is this genius technique that takes multiple analog or digital signals, think voice calls, video streams, or data packets, and cleverly combines them into one single composite signal. This bundled powerhouse then travels over a shared medium, like a fiber optic cable or wireless airwaves, making everything more efficient. Why bother? The motivation is pure economics and smarts. Most communication mediums, from copper wires to satellites, pack way more bandwidth capacity than any one device could dream of using alone. Without multiplexing, that extra space sits idle, underutilized and straight up wasted, like reserving a whole theater for one viewer. It's not just inefficient, it's costly in terms of resources. Now, the process itself is elegantly straightforward, almost like a relay race. At the starting line, the multiplexer, or MUX for short, acts as the packer, grabbing all those individual signals from their sources and merging them into that one composite signal. This unified stream then races down the transmission link. At the finish line, the demultiplexer, DEMUX, steps in like a skilled sorter, carefully separating the signals back out so each reaches its rightful destination without a mix-up. And the key benefits? Oh, they're game changers. Multiplexing dramatically boosts data throughput, letting you pump more information through the same pipe. It slashes infrastructure costs by minimizing the need for extra physical cables. Fewer wires mean less digging, less maintenance, and greener builds. Plus, it enables scalable resource sharing, so as your network grows, you can add more users without ripping everything up. For a real-world example that hits home, think about your cable TV setup. Those networks beam hundreds of channels, sports, movies, news, all at once over a single coaxial or fiber cable, thanks to frequency multiplexing we'll cover soon. It's multiplexing making entertainment effortless. Did you know? This whole idea traces back to the 1870s in telegraphy, where inventors figured out how to send multiple messages over one wire simultaneously. From Morse code to streaming Netflix, it's the same clever trick evolving. Multiplexing isn't just tech, it's the foundation of connected life. Ready to see it in action with frequency division multiplexing? Let's tune in next. Shifting frequencies now. Welcome to frequency division multiplexing, or FDM, the analog wizard that slices up bandwidth like a DJ assigning tracks to different radio stations. We're talking dividing the available channel bandwidth into distinct, non-overlapping frequency channels, so multiple signals can jam together without the chaos of overlap. Let's unpack the concept and how it works. Picture the total bandwidth as a big pie. FDM cuts it into separate slices, each tuned to a unique carrier frequency. Your source signals, say, audio or video, get modulated onto these carriers, shifting them to their assigned frequency bands. Then, all these modulated signals transmit simultaneously over the shared medium. At the other end, filters pull them apart based on frequency, like tuning your radio dial. But no perfect pie without a few crumbs. Enter guard bands. These are small, intentional gaps in frequency between channels, acting as buffers to prevent signals from bleeding into each other, causing interference or crosstalk. Yeah, they nibble a tiny bit of bandwidth, but it's a small price for crystal clear separation. Without them, it'd be like neighbors blasting music at the same volume, total noise fest. The process flow is a smooth assembly line. Start with your source signals feeding into modulators, each getting a different carrier frequency. Those get added or combined into one composite signal, which heads out over the transmission medium. On arrival, bandpass filters, Think frequency-specific sieves. Isolate each channel, routing them to demodulators that strip away the carrier and restore the original signal. Clean and efficient. Glance at Figure 1. That bandwidth allocation graph shows it beautifully: blue, green, orange, and purple bars for channels 1 through 4, with white guard bands in between, plotted against frequency on the x-axis and amplitude on the y-axis. It's like a colorful spectrum where each hue owns its lane, preventing any crosstalk drama. Now, analysis time. The pros and cons. Advantages: it allows true simultaneous transmission, no clunky synchronization needed, and it's super efficient for analog signals like radio broadcasts or phone lines. Icons here nod to real apps: radio waves for AM, FM, satellite dishes for space comms, and cable TV for multi-channel magic. On the flip side, disadvantages include complex analog hardware that's tough to build and tune, those guard bands wasting a sliver of capacity, and vulnerability to noise. Electromagnetic interference can muddy the frequencies like static on an old radio. FDM's been powering broadcast TV and cellular tech for decades, but it's giving way to digital siblings. Up next, time to slice the clock with TDM. Time to get temporal. Enter time division multiplexing, or TDM, the digital maestro that shares a channel by carving time into discrete slots, like scheduling rapid-fire turns in a busy conference room. Unlike FDM's frequency splits, TDM's all about when signals get their say, making it a staple for digital networks. This is firmly a digital technique, with two main styles: fixed and dynamic time slot allocation. The diagrams here visualize it perfectly. On the left, fixed TDM shows a timeline with green and orange frames, empty slots glaring in yellow. On the right, dynamic packs blue slots tight, no waste. Starting with fixed allocation, synchronous TDM. Each device gets pre-assigned, dedicated time slots in every repeating cycle, regardless of whether they have data or not. It's like reserved seating, predictable and straightforward, with fixed timing that skips per slot addressing overhead. Implementation's a breeze, everyone knows their turn, no surprises. But inefficiency rears its head. If a source is idle, that slot still transmits empty, wasting precious bandwidth. Look at those orange empties, they're like ghost passengers on a train. Flip to dynamic allocation, asynchronous, or statistical TDM. Here, slots are doled out on demand only to devices with data queued up. No reservations means no empties. It maximizes channel throughput, especially for bursty traffic like web browsing or emails that come in spikes. Efficiency shines, but complexity creeps in. Each slot needs addressing info to know who's talking, plus sophisticated buffer management to juggle queues without drops. In the visuals, synchronous frames drag with gaps, CH1 data, CH2 empty, etc. While asynchronous frames fill smartly, CH1, CH3, CH2 repeating as needed. Pros for sync: reliability in constant streams like voice calls. For async, bursty data wins, think ISDN or modern packet switching. TDM's everywhere, from T1 lines carrying phone calls to cell towers multiplexing texts. It's about democratizing time. Everyone gets a fair shot, but smartly. With topologies on deck, let's wire up how these signals travel next. Alright, network architects, time to blueprint your digital city. Network topologies overview: the physical and logical arrangement of nodes and links that dictates how data dances between devices. Topos, from Greek, means place, and where things connect massively impacts performance, install costs, scalability, and how well your net bounces back from faults. Choice here is everything. Wrong topology, and your network's a tangled mess. Right one, and it's a symphony. We're spotlighting three classics: star, bus, and ring, each with quick stats on reliability and cost. Star topology: all devices connect directly to a central hub or switch, like spokes on a wheel. One node's failure, others keep humming. Reliability: high. Cost: medium, more cable, but worth the stability. Diagram shows computers fanning to a blue hub. Bus topology: devices tap a single main backbone cable, data broadcasting like a subway announcement. Simple linear setup. Reliability: low, one break halts all. Cost: low, minimal wiring. Visual: nodes teed off a straight blue line. Ring topology: devices chain in a closed loop, each to two neighbors, data circling one way like a merry-go-round. Equal access, no broadcasts. Reliability: medium, Cost. Low. Icon. Curved chain of computers. The overviews nail it. Stars most common for offices, easy adds, bus simplest for tiny LANs, cheap but fragile, ring deterministic for steady flow, token passing prevents jams. Figure 1's ring sketch with 6 workstations in a clockwise loop screams sequential elegance. Topologies your foundation, star for fault-tolerant growth, bus for budget bootstraps, ring for collision-free equity. Impacts. Star scales easy but hubs bottleneck, bus cheap but noisy under load, ring efficient but break prone. Pick based on your crowd, small team. Bus, enterprise, star. Let's dive deeper into the star next. Zooming into the crowd favorite, star topology, your centralized hub and spoke network architecture, the go-to for modern LANs because it's reliable and expandable, like a sun with planets orbiting without drama. Figure 2 captures the essence. Nodes, computers and workstations, each with dedicated lines arrowing to a blue central hub or switch. No shared paths, everything funnels through the core. Architecture breakdown, every device enjoys a point-to-point link straight to the central controller, be it a dumb hub, broadcasts to all, or smart switch, direct routing. The controller's the traffic boss, data from device A to B. It relays through the center, no detours. This isolation means signals don't interfere, pure dedication. Scalability and management, top-tier ease. Installing, plug and play one cable per device. Reconfigure, swap a connection without downtime, add a printer, remove a laptop, network shrugs. No rip and replace nightmares. Analysis pros, robustness rules, one link fails, others unaffected, unlike chain reactions elsewhere. Fault isolations a snap, lights on the switch pinpoint issues. Performance soars with switches forwarding only to targets, ditching broadcasts. Icons highlight, central controller in blue, dedicated links in purple. Cons, that hub's your Achilles heel, single point of failure means if it tanks, power surge, overload, the whole star dims. More cabling than bus or ring hikes install costs, though twisted pair Ethernet keeps it reasonable. Stars dominate Ethernet offices and Wi-Fi access points for good reason. Balance of speed and simplicity. From home routers to data centers, it's the topology that scales with you. But for linear savings, let's bus along next. Stripping it down to essentials. Bus topology, single backbone cable architecture for linear connections, the budget backpacker of networks, great for small, simple setups where cost trumps complexity. Figure 3 lays it out. Nodes, workstations, teed off a central blue backbone cable, terminators capping both ends like bookends. Data arrows show broadcast flow. Backbone architecture, one coaxial cable serves as the shared highway. Any node transmitting, signal blasts the full length in both directions, efficient for shorts, but echoes lurk. Signal terminations non-negotiable, those end terminators absorb outgoing waves, quashing reflections that bounce back and garble data, like echoes in a canyon ruining a shout. No caps, interference city, corruption guaranteed. Broadcast nature, packets holler to all stations, each checks the address, match. Process it, no, ignore, like junk mail, efficient filtering, but heavy traffic means everyone hears the noise, slowing the bus. Analysis, advantages glow green, easy, cheap install with minimal cabling, one spine feeds all, ideal for small labs or legacy Ethernet. Icons, red terminators required, blue broadcast transmission. Disadvantages byte red, cable snaps. Entire net dead, no redundancy. Heavy loads crawl as signals collide and retry. Troubleshooting, hunt the line like a faulty fuse, tedious. It's fading for good reason but teaches shared medium basics. Bus, proof less can be more, until it's not. For looped reliability, ring up next. Circling back with elegance, ring topology, closed loop architecture with sequential data forwarding, where info passes baton style around a circle, ensuring fair play without the bus's shout fests. Figures 1 and 3 diagram it crisply, 6 workstations in a unidirectional clockwise loop. Figure 1, each node linked to 2 neighbors. Figure 3, arrows showing data flow. Circular structure, closed chain, no ends, each device wired left and right, forming an unbroken path. Breaks the linear mold for true connectivity. Data transmission, unidirectional flow only, clockwise or counter, your call. Each node doubles as repeater, receives, regenerates, boosts weak signals, checks address, forwards if not theirs. No broadcasts, targeted relay. Predictable access, token passing often rules, a token circulates, holder transmits, preventing bus-like collisions. Everyone gets equal turns, ideal for steady loads. Icons underscore, blue unidirectional arrow, purple token passing, green repeater logic. Analysis pros, equal access, zero collisions, token enforces order. Efficient under heavy loads, less cable than star, daisy chain savings. Great for token ring legacy nets. Cons, single break, cable cut, node fail. Ring opens, net halts, dual rings mitigate, but basics fragile. Troubleshooting traces the loop, time suck. Adding nodes. Break the ring, insert, reclose, service dips. Ring, sequential smarts for collision haters, but redundancy's key. From early IBM tokens to fiber rings, it's orderly flow done right. Now, layer up to data link drama with ALOHA. Layer 2 showdown, data link layer and ALOHA protocols, architecture breakdown and random access mechanisms ensuring reliable node-to-node delivery over shared media, without the higher layers' global worries. Goal, error-free handoffs across the wire. Figure 1 stacks OSI, network layer, L3, atop, data link, L2, with LLC, flow, error control, and MAC, access, addressing, sublayers, down to physical, L1. Data link sublayers, LLC, logical link control, upper layer liaison, managing flow, pace data, error checking, CRC detects baddies, frames sync. MAC, medium access control, the referee, dictating shared access to dodge collisions, plus addressing via MAC-IDs. Pure ALOHA concept, fire and forget, transmit whenever ready. No ACK in time, collision assumed, random backoff, retry. Collision risk, high, vuln windows full packet time both ways. Efficiency caps approximately 18%, simple logic but wasteful in crowds. Slotted ALOHA levels up, time diced into slots, transmit only at slot starts, needs sync clock. Vuln window halves, slot duration, efficiency doubles to approximately 36% better throughput, though sync adds overhead. Side by side, pure, continuous time, high risk, simple, slotted, discrete slots, sync required, superior flow. Visual, pure shows overlapping bursts, red stars for collisions, slotted aligns neatly. Pure birthed from Hawaii's radio nets, ALOHA, slotted refined it. Foundation for Ethernet, Wi-Fi, random access tamed. One more, CSMA, CD's collision copper waits. Collision chaos no more, CSMA, CD, carrier sense multiple access with collision detection, the MAC protocol turning shared wires into courteous convo, Ethernet's original guardrail. Flowcharts the star, standard IEEE 802.3 logic, listen, blue, idle check, diamond, transmit, green, detect, orange jam, back off, yellow, complete, check. Step 1, carrier sense, listen, node eavesdrops on channel, idle. Green light, this, listen before talk, etiquette nips many collisions in the bud, polite, proactive. Step 2, transmit and detect, go time, blast data, but crucially, keep listening mid-send for interference. Half duplex magic, sense your own transmission overlapping intruders. Step 3, collision response, smash detected, instant halt, send jam signal, short burst alerting all, abort. Clears the air, informs the crowd. Step 4, random backoff, cool off with exponential backoff, random wait, doubles each retry, before reattempt. Minimizes repeat pileups, smarter than fixed delays. Persistent strategies flavor it, 1 persistent, aggressive, idle. Transmit now, high collisions. Non-persistent, cautious, idle. Random wait, recheck, low collisions, high delay. P persistent, balanced, idle. Transmit with probability P, e.g., 0.5, balancing risk and weight. CSMA, CD ruled 10/100ths of a megabit per second Ethernet, full duplex, switches evolved it out, but principles live in Wi-Fi's CSMA, CA. It's the sense, send, save trio keeping shared media sane. Wrapping with takeaways next. As we wrap this network fundamentals whirlwind, from multiplexing magic to topology blueprints and protocol peacekeepers, Let's crystallize the key takeaways, your cheat sheet for efficient data comms. Efficient bandwidth use, multiplexing, FDM and TDM, bundles signals into single channels, maxing capacity while slashing infrastructure costs. No more lonely cables hauling one stream. Icons pulse, frequency waves and time slots sharing smartly. Structural impact, network topologies, star, bus, ring, blueprint scalability, fault tolerance, and maintenance ease. Star for robust growth, bus for cheap simplicity, ring for ordered flow. Choose your skeleton wisely. Reliable delivery, data link layer ensures error-free node-to-node transfers. LLC cops flow and errors. MAC handles addressing and access, the L2 duo gluing physical to network. Conflict resolution, MAC protocols, ALOHA, CSMA, CD, act as traffic rules, managing contention to zap collisions in shared environments. Pure ALOHA's Wild West to CSMA's refined highway. The big picture, designing killer networks demands aligning protocols and topologies to traffic patterns and mediums, bursty web. Statistical TDM plus slotted ALOHA. Constant voice, sync TDM plus star. Constraints like cost or scale. Bus or ring tweaks. You've got the fundamentals. Multiplex to multiply, topology to structure, protocols to police. Apply this, and your nets hum. Thanks for riding. Like, subscribe, comment your topology pick. Episode 2 drops soon. Stay connected.